My name is Bart Ney. I am the Communications Manager for the Toll Bridge program here in California and the spokesperson for the Bay Bridge. I'm going to be addressing you today about load transfer for what will be the world's largest self-anchored suspension bridge. We're also going to be bringing up Dr. Brian Maroney, who is the Deputy Program Manager for the Toll Bridge program and one of our key designers on the bridge, who will go over some of the steps that are particularly involved with load transfer. What we want to do today is kind of show you through animation what some of those steps are that we're about to embark on for something that's going to be very historic. Over the next 3 months, we've already begun the testing phase of load transfer. We're going to be shifting approximately 35,200 tons of steel from temporary works that we've placed out there that are the size of the original Bay Bridge. From those truss structures up into a cable system, the main cable of which weighs over 5,000 tons. So these are big numbers. That 35,000 ton number, that's like almost 5 Eiffel Towers that we're going to be lifting. So that gives you some idea of the magnitude of what's going to happen. Now, we'd like to thank the folks, our partners here at the Aquarium of the Bay, who have been running some of our features on some of the work that we've been doing on the Bay Bridge to allow us to have this event here today, because we really wanted to show you on a big screen and give you a little bit more impact of what this operation really is. So thank you very much for the opportunity to do that today. This presentation is being brought to you by the Toll Bridge Program Oversight Committee, which is Caltrans, the Bay Area Toll Authority, and the California Transportation Commission. So go ahead and roll it, Paul. We're going to be very informal talking to Paul today. These are the main elements that are involved. Hydraulic jacks doing the work, the suspender ropes that are tied on to the main cable, and then the temporary works are what's holding the bridge right now. That's where we're transferring the load from. So basically, the operation is going to be pulling that main cable into place and lifting the bridge up. Now, we want to take a step back and remind everybody, what is a self-anchored suspension bridge? This isn't new technology. It's over a century old. There are 30-some-odd SAS bridges around the world. This will be the largest one ever built. Ours is also a little unique in that it has a single, centrally placed main tower and one main cable that is anchored on its eastern side, heading towards Oakland over by the Skyway. It goes up and over the decks where traffic will be running over the top of the tower, and it wraps around. I'll use the laser pointer. It wraps around the back end of the bridge at Yerba Buena Island, returns to the top of the tower, and anchors on this side. So self-anchored suspension bridge basically means that instead of having this main cable that's doing all the lifting right here, anchoring down into the ground, or into a big anchorage out in the middle of the water, like on the western span of the Bay Bridge, the bridge is anchored into the very deck that you're driving on. So the cables are in tension, the deck pretty much in compression. These forces are balancing themselves out, translating down through the tower. Key elements are, of course, the anchorage on the eastern side where the cable comes in and fans out, and on the western side over by Yerba Buena Island, the wraparound where we have a jacking saddle. Now, the process for building a self-anchored suspension bridge, if you keep it moving, Paul, we had to place false work or temporary works. This is much bigger than false work, which is normally wood, that were about the size of the existing Bay Bridge. So we had to build a bridge. We had to build 2 bridges in order to get this one together. So that was done, and then we placed the deck segments one by one. There's 14 in each direction, a total of 28, and the tower section had to be erected as well, and 5 different lifts. The tower is actually made up of 4 independent legs, so you can think of it as a stool almost, that all had to be put in place. Once that was in place, we could go to the placement of the main cable. A footbridge had to be erected so we could put our craftspeople up there to help get the main cable in place. And then cable bands, which are the saddles that we will have the suspenders actually going around. 114 of them had to be placed out on the cable, and then the suspenders themselves had to be put in place, connected together, and then we transfer the load. That is what we're here to talk about today. That is the operation that has begun out on the San Francisco Bay. And of course, once the load's been transferred, we will remove all of the temporary works and we'll have our new bridge. So now we're going to run through the simulations. And we're going to go back in time a little bit. This is the area that we're talking about. This is our self-anchored suspension bridge, Yerba Buena Island. So some of the operations that we already went through, well, we had to pull the tower back towards Yerba Buena Island so that when it came the time that we were loading this thing, we could release it so that it didn't bend in the opposite direction. Then we had to place the cable, and that was no easy feat. This is the first time this operation had taken place. We had to use 2 different hauling systems to pull basically strands, 137 strands. Each strand contained 127 wires all the way around the bay and back to the eastern side of the span. So there you can see that's what the main cable is made up of. These strands, each one of those strands has 127 wires, 17,399 total. Then once that's in place, you don't have that perfect cylindrical form, so we have to compress it. We use compressing machines from the top of the tower, ran them down so that we could get rid of the voids, the spaces that are in between those, and compress it into a strong cable. Then you saw a little shot of the anchors. They're plated over. And then the cable bands. There are several different types of cable bands because they're at different places on the main cable that allow the suspender ropes to hang over the top of them. Each one precisely engineered to allow for the motion that's going to be taking place with load transfer. Then you got to get the suspender ropes in place. This is one of the ways that we did it. The ropes, the wire ropes, arrive in spools. They're lifted over the top. Now, we have not animated people in this, but several crafts are working here, iron workers in particular, to make this all happen. There's a lot of other equipment, but this is the basic concept of what we did to get the suspenders in place. About 200 suspender ropes on 114 different saddles make up this bridge. And then the suspender ropes are connected into our jacking mechanism. Then we're ready to move into load transfer. Now, load transfer is complex. Paul, if you can pause it right there. Basically, again, what we're talking about today is taking the weight off of the temporary bridge that we had to build and placing it onto the cable system. That's as simple as it gets. We have to do this, though, go ahead and run it, Paul, in 3 phases. So the first phase, which is what we're at right now, our contractor and engineers have very carefully selected 114 different ropes. Then the second phase has these ropes that are close to the tower, and then the third phase, the final ropes that are distributed throughout the system. At that point, all of them have been connected, all of the load has been transferred, and what Dr. Maroney will tell you is that the first set of ropes are going to be, Paul, if you can pause it right there, are going to be handling the largest loads that they will ever see right here at the beginning during this operation. So at the highest level, this is what we're talking about today. It's an amazing historic moment for the Bay Bridge. We're lifting an unbelievable amount of weight, placing it onto this cable system in 3 phases. And now what we want to do is I'm going to ask Dr. Maroney to come up here and explain a little bit more in detail what happens. But what we've tried to do with this animation, and please take this to heart because it would be easy to get lost here, this is all happening about the same time. You're going to see this presentation in sequence. We're going to take you from one box to another. But keep in mind that our crews are out there doing all of these steps at the same time. So when we jump from one box to another, you're literally going back in time, seeing the operation from a different perspective.
Okay, first thing I want to give some reference here. If you think about the Golden Gate Bridge, you walk out on the Golden Gate Bridge or San Francisco, Oakland Bay Bridge on the west spans, you see where the cables come down at the end of the bridge. It's about a 3- or 4-story concrete building. Okay? That's what's holding down those cables. And that 3- or 4-story concrete building, it really doesn't move as load transfer takes place on a regular suspension bridge. And how does that take place? You know, one superstructure unit at a time usually comes in on a ship and it's lifted up one at a time, and it happens very slowly. Okay? It can take as long as it takes to put all the pieces up and then the concrete decks to go on top of it. So it takes a pretty long time. And the cable system is anchored down to huge concrete buildings, many times going deep, deep, deep into the ground, sometimes into rock, sometimes into a piling system, depending on the different type of bridge. Here, we've got something, quite frankly, infinitely more complicated. it doesn't have that 3 or 4 story concrete building. That 3 or 4 story concrete building is right here. And architecturally, it was desirable. It was desired to have a single line going across the bay. So that little bulge right there, that's all we have. It's 5 meters deep. So this is almost a modern engineering miracle to work with the architects to develop what those architects envisioned and what the community decided looking at the different lines on the bridge, et cetera, that they wanted. Now, to have the self-anchored suspension bridge, we're replacing those large concrete buildings with this superstructure that's 1/3 of a mile long. Now, because it's a superstructure that's 5 meters deep and it's very, very long, okay, it's not a concrete building that's not going to move. Okay, it's actually going to move. So there are multiple things going on, as Bartney mentioned, okay, but I want to get across to you, it's a moving system. On a regular suspension bridge, everything you put up, it really doesn't start moving until the cable itself starts moving. But the ends of the cables, they don't move. Here, lots of things are moving. Okay? So that means everything has to be done all at once. There's no such thing as doing one thing at a time. You can't lift this superstructure up off those temporary towers. You can't lift that without starting to load up the superstructure. So what you're lifting up is actually moving, right? So this heavy lift that Bartney just described, it's a moving lift as it's going on. Plus, the tower that the cables are tied to, we're going to be managing that moving. American Bridge Floor, the company that's doing this for us, okay, they're managing that moving too. Okay? At the same time, these cables, you can't put all the cables up all at once. So there's had to be a designed, carefully evaluated lifting scenario where we lift up pieces of it at a time. You can't do it all at once. Now, what that means is that's kind of interesting. It means some cables, as we lift up the bridge, Bartney described and showed you visual where we've lifted up the bridge and only some of the cables are connected, right? So that means these suspenders, some of them, the ones that are being lifted up at early stages, some of them are going to be up to double their load during service. And that's not uncommon for during construction, okay? A part of a bridge or part of a structure to see its greatest demands during the erection process. And we actually get a great load test, right, on some of these. Now, we also have very good, comfortable factors of safety. We knew this, we anticipated this, we planned this. So some of the suspenders, we have something like a 25, we have something like about a, we're only using something like 25% of the capacity of these suspenders at live load service conditions. So even if we take it up, we still have a comfortable factor of safety even in construction. Okay, so I'm going to ask Paul to walk us through these, and I'm going to describe them as he turns them on. Okay, this is a shot where we see the contractor has pulled over the system, and would you pause please for me, Paul? Okay, what the contractor's done is the suspenders are up, as Bartney described, they're hanging, and there's been a system of jacks and rods and connection devices onto the cable, and what they've done is they've lifted the cable pulling system up into the ropes, connected on to them, and then hydraulically down here pulled those rods and that cable over. Now what it did is it moved the main cable over, and the main cable moves about 10 meters. It translates about 10 meters. So I was trying to describe that everything's going on all at once. Okay, what we're trying to do is lift this box up off of these temporary works, but we're also having to do that by pulling against the cable. And the cable, even though it's very, very strong, over 17,000 wires, each one of those wires is 5 times the strength, more than 5 times the strength of regular 50,000 KSI steel. So this is very, very strong, but it's still flexible. So this cable moves a lot, many, many, many feet, just to get this to go up a few feet. Okay? Okay, so next, go ahead, Paul, please. Okay, now, here's a shot where you see the same thing, just a close-up. These are the rods. These are temporary. These are the permanent suspenders that are coming down. They're 2 400-ton jacks that are being worked, reset, worked, reset, worked, reset as they pull. Okay, there's the rods. Okay. These are the wounded suspended wire, suspended rope. Okay, this is the end block. These have a hole in them. A threaded rod goes in and nuts go on the bottom to lock it in. Okay, the shims go in, we lock it into place. This is a shot while this is all going on, if you were underneath, as the box is coming up on the order of, it varies. Some locations near the tower, it's not even going to lift up off the temporary works. Other places, it's going to lift up as much as a meter separating between the two. On average, something like half a meter up. Okay? While the cables are moving, Bart, I always like to use metric, but you have the English imperial numbers memorized. 30 feet by 16 feet, right? One way over, one way down. Okay? Now, underneath the bridge, I described to you that the box is actually going to be shrinking. It's going to be, it's not shrinking, it's elastically shortening. Okay, if you have Paul, could you pause? If you have a rubber band, right, and you put load on it, it stretches, right? So there's a relationship between putting a load on something and how much it stretches. Same thing happens in compression. If you squeeze something with a force, okay, it gets shorter. As load is transferred from the temporary works to the box going into compression, the elastic shortening from that load transfer process is going to elastically shorten this box under that load, okay, by about a foot. Okay? Go ahead, Paul. Now, underneath, we can't connect the new E2 pier, that's the eastern pier on the east end of the SAS. We can't permanently connect it yet because we've got to allow for that shortening. Okay? So what we have to do is we have to not connect it, okay, until after it's shortened, and we've got some temporary sliding systems. Now, way back on the other side, on the west side, we want to have, as we tighten and load transfer, we want to have a nice, even distribution of load in that cable. So we've got a jacking system on the west end to push out the cable, hydraulic jacks here and here, and these are shims. So as these jacks push it out, we put in spacers, shims, and then once we have it to the right space, then we put reinforcing steel, cast it in a rock, and it's set forever. That's going on simultaneously. All these things have to go on simultaneously. Up at top of the tower, as the tower moves, okay, these are the tie-back cables. Okay, we have to adjust for that flexibility up at the top, constantly managing as load gets transferred. Then there's cable protection, cable shrouds back on the west side to protect the cable. And with that, I think I'd like to ask Bart and Ada to come back over.
Thank you very much, Brian. But what do you take away from this discussion? There are a couple of key points. One, this is a very large milestone for the Bay Bridge. It's one that we've been waiting for a number of years. And it's been very carefully engineered to ensure that it is done correctly. Two, there has been a notice to mariners out for a long time not to go under the self-anchored suspension bridge because a number of operations have been taking place. We are strengthening that message to boaters right now. Individual pleasure craft should not go under this bridge during this time. The notice to mariners has been out for months, but it obviously attracts people to want to come under it and see it. There are going to be a lot of crews, 8 different crews working on this for the next 3 months until we get this done. And that means there's a lot of potential for tools to fall and that type of thing. We want to keep people safe. Do not go under this bridge while we're doing this work. And then finally, we're still on schedule to open this bridge to the public, Labor Day 2013. This is a key operation for us to get completed, to make it through, so that we can do all of the finish work to get the bridge open. So those are the main points that we want to get across today. I know one of the questions that will normally come in a presentation like this is, well, what's next? So we thought we'd just take a couple quick minutes here to show you what's next. You can put your pens down if you want to. This is just kind of to answer that human question that's going on. What do you do after this? So Paul, roll it. The next time we get together, we're going to be talking about the load having been transferred and wrapping that cable. So one of the props that we brought today is this S-wire wrap that we use to go around the outside of the cable. After the bridge has been pulled down, it's in its final geometry, it's now safe to wrap it up and keep it protected. We use zinc-based paste on the inside, we would use the wrap to keep corrosion out, and then we paint it. And so that's what that operation is going to be looking like. Now, there's a little bit of positioning that we'll have to do between the bridges. It's never going to be absolutely perfect out there in the real world, but thematically what we're going to be doing is lining up the self-anchored suspension bridge, which is kind of on the left over here, and the Skyway, on the right using these strand jacks in various different configurations. The hinge pipe beams, one of our innovations on the bridge, these 60-foot long, 6-foot diameter structures are going to be slid and connected in to help protect from earthquakes in this critical joint between these two different structures. They're locked down on one side over on the self-anchored suspension bridge. They allow movement on the other side. Again, there's not going to be a test on this. This is just what we have left. And then we'll be able to remove some of the temporary works again and place the joints that are actually going to be a little different than this. They're not going to go all the way across. They're going to be individual for lanes to allow us to remain open if we need to replace them. Place a little more hardware, complete the shrouding near the anchorage where the cable actually comes back and ties in. And then Dr. Maroney was talking about this a little bit. The bridge has to move. Once we know the bridge is done moving, we can pin in the bearings that allow the bridge to move and the shear keys that control that movement in certain directions, and make sure that they are strong in the position that they need to be in when we're done moving the bridge around with load transfer. So these are some of the different operations that we'll be explaining later. And then temporary works, again, can be removed, and we can start looking like the bridge we were intended to be. We've got a footbridge up there that we're working on right now. That will come down. The false work on the tower will come down. This will be the configuration that will look like on opening day. We'll still have some of that false work underneath it. And then legacy-wise, after we take down the old bridge, which is a completely different topic that we'll be addressing you soon on as well, this is what we will have. The world's largest and most beautiful self-anchored suspension bridge. So that's our presentation today. We're going to bring we'll bring the house lights back up. Are there any questions that you all have out there right now?
I guess this signals that you think that everything's okay, and then yes?
Well, first of all, you have to remember my perspective. I'm a technical engineer. That's what I do. I supervise, I manage also, but my focus is technical. And there are other parameters involved in this issue, and that's quite frankly for professionals in those areas to decide. But I can tell you technically, I am satisfied with this. And if I wasn't, I would be stopping it. Technically, I'm very satisfied. Also, you have to remember my assignment as Toll Bridge seismic retrofit chief bridge engineer is to race to seismic safety. That's right out of the Governor's Board of Inquiry in 1989. After the Northridge earthquake, California Department of Transportation got hit pretty hard about not going fast enough. That's how the toll bridge program got created. From the criticism in '94, go, go, go. We're racing to seismic safety. I think they even named the report, "The Race Continues," the continuing challenge. So my direction, and I work for Tony Anziano, the program manager, and he works for the director of Caltrans, and then they're all part of the TBPOC, Toll Bridge Program Oversight Committee, which is the folks that Mr. Ney described. Their direction to me right now is, Brian, you get that bridge up, you get it safe, you keep going, and right now they're saying, we trust you, we trust your team, and we still want you to have a seismic safety external independent peer review panel, just like the Governor's Board of Inquiry said we're supposed to do, and that's what we've been doing. We've got people like Dr. Sibley from UCSD, we've got people like Dr. Idris from UCD. We've got people like John Fisher from Lehigh. These are people who are in like the Academy of Science. These are the best engineers in the world. I feel the people looking over my shoulder and the advice that they give me or tell me, rethink this one or you know what, this is the right way to go, 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 go. I feel like internally I've got checks. I don't do anything once. I do everything at least twice. Then I also I have a responsibility to show them things. And then they also have freedom to look at anything they want. Anytime they say, I want to go look at this, I have to say, yes, sir, independent peer review panel, I'll take you there. And they go out in the field, everything. So I'm feeling really good about this, and I'm following exactly what my orders are now. Head down, get this job done safely to the workers, get the public safe, seismic safety, and as Dr. Sibley said, earthquakes don't wait for anything. And I just stand out there and I go, this is great work, let's keep going. And I look at that old bridge that actually had a partial collapse in 1989, and I'm thinking, that bridge has a problem. This bridge doesn't have a problem, and I can technically show it. So that's my perspective.
Let me step in there. Okay, and thank you for that question. That's a very natural question to come up today. We are not going to iterate the testimony that's already been put into that hearing, other than what Dr. Maroney has just said. I think our director, Dr. Maroney, the other witnesses made it very clear that our belief is that the Bay Bridge is safe and strong. And that's how we're able to go ahead and do landmark things like this. But we are going to, in the statement that we put forward yesterday, continue to work to prove it to the public that the bridge is safe. When we do construction work, any operation in the field, there is multi-level peer review as we go forward. First, the design is reviewed, and I'm not talking about the design of the bridge, I'm talking about the design of the operation. We get clear on what we're going to do before we go out there. And then when we actually get into the field, we have our own certified Caltrans engineers and inspectors that watch the operation. We have an amazing contractor, American Bridge, that built the original Bay Bridge, and Floor Enterprises, which is internationally renowned, doing this work. So they put their best and brightest on it. We're right there with them. The Toll Bridge Program Oversight Committee was formed so that we have joint oversight on the bridge as we move through every single day and night, and that's when this project takes place, during the day and during the night. Our partners from the Bay Area Toll Authority provide additional inspection during these operations with their own inspectors, their own reports. So this goes on as the operation takes place.
Those jacks, Bartonet's visual here where you actually saw the suspender rope being pulled down, okay, that's done with jacks. Our construction staff, actually just yesterday we were going over, once again, we're going to have one engineer of our engineers, the owner's engineer representing the people of the state of California, at every single one of those stations watching to make sure as it's pulled down, okay, the jacks never go over a certain load, which would potentially start to eat into that factor of safety that we've got on the suspenders. So we've got owners watching, one per jack system, inside a control center. I expect to have one of my lead construction engineers, maybe the resident engineer or the structure rep in charge of cable systems. Contractor will have something that looks like an air traffic control center. And every one of those working cables, the transferring load, right, where the suspenders are coming down, there'll be a small construction team led probably by an engineer for the contractor at every single one of those. They'll have radios, and they'll be, at a certain time, when the time is right, they'll say, go. And on phase one, 8 different teams will be coordinated through this, if you will, almost air traffic control center, and they'll say go. Now, the contractor has designed a very thoughtful scheme where those 8 different teams, it doesn't matter. The system is insensitive to, do you go up a quarter, do you go up a half, does team 8, does team 7? So it's insensitive. So, but because we know that, we've watched that, we've approved their procedures, we know that we have the right amount of people looking for the right thing. So they've prepared very well. They're going to be, they know the displacement they have to pull it down to. Those suspender ropes, those are literally sensitive to millimeters. So they're very specifically designed for the weight of this bridge, the load it needs to carry. So we're going to be pulling them down, putting them into place, and we're going to be using jacks, and those jacks are actually calibrated. Before somebody gets to use a jack out on a state bridge, we actually force them to go in a laboratory and verify that the oil pressure that goes in actually correlates well with the load. So contractor, first of all, planning. That's the first level of supervision. It's been going on for years. Second one, the contractor has a team. There's a lead person. There's a control center for the contractor. Caltrans, or the people of the state of California, will have an engineer at each one of those load points, making sure the load never goes higher. And then we'll also probably have one engineer in the control room, in and out, just monitoring and making sure things are going as they will. I have great confidence in this team. ABF's done a great job here.
Beyond the engineers that work for Caltrans that put their stamp on the line when they do this thing, there has been 3 levels of independent review that have gone on for the construction of the foundation that's going to support this lift, and for just about every operation that we've done on the Bay Bridge. Those levels of review are the Toll Bridge Program Oversight Committee, our partners at the Bay Area Toll Authority. It was the assembly that told us to come together, and they provide additional inspection independent of our own Caltrans engineers that have their stamps on the line for every operation that's done. They're out there side by side with us, but they are independent of us so that they get the same information. They sit in the same meetings, they watch the same operations, they develop different reports, they're right there next to us, and that is being done because we were told to do it, and it's been very successful to date. You know, I think Senator Simitian talked about a little bit of needed friction between the two. Sometimes that exists. It is healthy, and that's how we know that we have gotten the independent review we have beyond that. Dr. Maroney explained a little bit about the Seismic Peer Review Board. This is the Hall of Fame of engineers internationally in these different areas that have been commissioned to watch the project and work with us. And then beyond that, you have our own Federal Highway Administration. This is at the national level. Their engineers reviewing the work that's been done. You can't get better independent review than that. That review has been done. We stand behind the Bay Bridge. The Bay Bridge is safe, and we're ready to move forward, and we're moving forward. What I'd like to wrap with is what happened here today. Okay, we came before you out in a public space and discussed the largest operation that we will ever do on the Bay Bridge, and we've done some big ones. We have done this immediately following a hearing so that we have got complete transparency on the operations that are going out there. We have the best engineers in the world working on this job. We have the best third-party review that's possible on this job, and we are going to do big things, and we're in the middle of doing big things.